So in this lecture we compute a particular example, that is magnetic field on the axis of a circular current loop. Now you are given a circular current loop, so this is the circular loop and this is the axis of the loop. This is the axis right here, so say this is the x-axis, and then you have an axis perpendicular to it. Say you have the y-axis right here and the z-axis right here. So this is the loop. So the current is in the loop. So you notice that the current is going in this direction. So we take a small ds vector right here. And we want to calculate magnetic field at this point P. So we want to calculate the magnetic field at this point. So r vector is the distance of point P from this ds vector. So this entire green line is r vector. You convert this r vector to a unit vector, which we denote by r hat. So r hat has the same direction as r vector, but its magnitude is 1. So you put it like this. So first thing is that the angle between ds vector and r vector is 90 degrees. So if this was just a plane and not a loop, so you would have ds vector and r vector like this, and the angle between them would have been 90 degrees. It still is. So now what you do is, this is the vertical axis, you tilt r vector so that r vector goes downwards. Now the angle between ds vector and r vector still remains 90 degrees, but now r vector makes an angle theta with the vertical axis. Now if you compute the magnetic field at this point, right at this point here, then you will see you're going from ds vector to r vector. That is our formula, that ds vector cross product with r vector is in the formula. So dv vector will always point upwards in this case because you're going in the anti-clock direction. So dv vector is pointing upwards. But once you tilt r vector, then the dv vector will also get tilted. It is still perpendicular to both ds vector and r vector, but now it makes an angle theta with the horizontal. So this is the case here. So at point P, the dv vector would make an angle theta with the horizontal axis. So this dv vector has two components. It has dbx and db perpendicular. So the radius of this circular loop is a, and this point P is at a distance x from the center of the loop. So this is the center of the loop. Now you see this is a right angle triangle with three sides. So you have r square is equal to a square plus x square. So what is cos theta? Cos theta is equal to, you always say it is adjacent side divided by hypotenuse. So adjacent side is a, hypotenuse is r. So this becomes a over square root of a square plus x square. And these results we are going to use. So we have just computed cos theta as a over a square plus x square. Now this is from the formula on the previous page. On the previous slide, we have seen that the small dB is equal to mu naught over 4 pi I ds sine phi over r square, where this phi is the angle between ds vector and r vector or r hat. So this is the angle phi, and we have just taken phi as 90 degrees here. As we said, we are always taking ds vector is perpendicular to r hat. So this phi is 90, so sine phi is just 1. So now you plug this in, you get dB mu naught I by 4 pi, and instead of r square you write a square plus x square. Now we only consider the component dbx. So dbx becomes db cos theta. Now we do not worry about the perpendicular component, because consider another point. Say there is another point here. So this point will also exert force on P. When it exerts force or magnetic field on P, this magnetic field is in the opposite direction. So now this is a dB perpendicular right here. So these two forces, this part and this part, cancel out. So therefore we only consider this part dBx. So dBx is just dB. You take dB and take cos theta, that is the horizontal component of it. You integrate, so you put a integration sign. So instead of cos theta, now you're plugging in the value a over a square plus x square to the power of half. So this you plug in here. So you get a here. You multiply a square plus x square to the power of half with a square plus x square. You get a square plus x square to the power of 3/2. So everything is constant here except this ds. So ds remains in here. And when you integrate this ds, you get 2 pi a. So this will come as 2 pi a. So you are integrating over the entire length of the loop. And the circumference of the circle is 2 pi a for radius equals to a. So you are integrating over this entire loop. So that becomes 2 pi a. Now you do the cancellation. You get 2 here. And a times a becomes a square. So you get mu naught I by 2 times a square divided by a square plus x square to the power of 3/2. And we are writing here hat on I because the way we have demonstrated, this is in the direction of the x-axis. The origin of the circular loop lies at the origin of the coordinate axis. So this is how you get this field Bx. Now at the center of the loop, x is 0. So you plug in x equals to 0. So if you plug in x equals to 0, you get B equals to mu naught I by 2 times a square to the power of a square times 3/2. This cancels out. This is a cube. You just get a here. So this is the value you get for magnetic field at the center of a loop.